Hello, Mathemaniacs. I'm the Math Edumacator, and today we're going to continue our discussion on set theory. In our last video, we introduced sets and elements, the collections of things, and things inside those collections. Today, we're going to begin our discussion on how we go from sets to numbers in mathematics. One of the limitations of the way we've discussed sets so far is that there's not really any way to compare them, except in the sense of saying that they're just the same. In set theory, two sets are equal if they have the same things in them. So if I have set A here, and everything in set A is in set B, and then for set B, everything in here is in set A, then those two sets are equal. They're the same set, basically. That doesn't leave us a lot of way to compare sets that are different. So we have to introduce a little more terminology before we really get into this idea of quantity. My friends and I are going on a picnic. Now, it was my job to make sure that I had snacks for everyone. So, I brought apples. Now, each person in our group has an apple. So, I have an apple for this guy. 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 And I have an apple for me. Now, in this instance, there isn't a person who doesn't have an apple. And there are not any apples left over. We have what we call a one-to-one correspondence between the set of people on the picnic and the set of apples that I brought. We can match up each element in one set to each element in the other set. This is where our notion of quantity begins. So with one-to-one correspondence, we can expand our notion of comparison. We can now compare two sets that are different by seeing if there is a one-to-one correspondence between them. However, this also has some limitations, namely that two sets either have a one-to-one correspondence or they don't. So we need to expand a little bit further. For that, we introduce cardinality. Definition: two sets have the same cardinality if there is a one-to-one correspondence between them. Because we know where we're going, we can kind of think of cardinality as the number of things in a set, but we're not there yet. Now this may seem like we haven't really gotten anywhere, because we're still talking about one-to-one correspondence. However, by using the phrase the same cardinality, that gives us the implication that there are many different cardinalities. And so now we have different things that we can compare, different quantities. In the example we just did, say I had a friend who didn't have an apple. Well, that would mean that I would need more apples in order to accommodate that friend. And likewise, if I had apples left over, that means I could have brought more friends along to eat them. So with cardinality, we now have enough structure to really establish this idea of quantity. So for any two sets A and B, I have three possibilities. Either the cardinality of A is equal to the cardinality of B, meaning that there's a one-to-one correspondence. The cardinality of A is less than the cardinality of B, which means I need to put more stuff in A to get a one-to-one correspondence. Or the cardinality of A is greater than the cardinality of B, meaning that I need to put more stuff in B to get a one-to-one correspondence. So equal to, less than, greater than. Now we have enough to compare, but we're still a little bit short. What do we call these cardinalities? What do we name them? And if we try to list out all these different cardinalities, how can we make sure that we don't miss anything? So what we're going to do is establish a simple procedure to generate all the cardinalities that we need without missing anything. So now we're going to try and list out our cardinalities, and we're going to start by building sets. So we've already talked about Venn diagrams. Now, if you want to list things that are in the set, then you put them inside squiggly brackets and you separate all the elements with commas. So we got my squiggly bracket right there. And, well, actually, I can't put anything in this. See, our little mathematical system is brand new. We don't have anything that we can put in it. Nothing is established yet. So, what I'm going to do is, I'm going to put nothing in it. I have this set with nothing. Okay. And when I want to list the cardinality of a set, then I put the set inside straight lines like this. Okay. So this is my first level of cardinality. And I can make a name for this, and I'm going to name it 0. So the cardinality of the empty set is 0. We write it like this. So we've established our nothing cardinality, but now we have something. We have this, our first number. So what if we put this number inside another set? So my new set has this thing in it. Now, this is clearly a different cardinality from my first set, the empty set, because this had nothing in it, and this has something in it. So, there's no one-to-one correspondence, must be a different cardinality. So, I'm going to name this cardinality. And this cardinality, we're going to call that 1. So where do we go from here? Well, now I have this thing and this thing. So I'm going to put these in yet another set. Now this new set doesn't have a one-to-one correspondence with this set or with that set. So this is a new cardinality, and I'm going to call this one 2. And we write it like this. So in the same way, we can continue creating sets that have all of the things or numbers that came before it. And each new set is going to have a different cardinality than the ones before it. So our next one would be the sets containing 0, 1, and 2. So 0, 1, and 2 has now this many things. So I'm going to call this cardinality 3. And the next one, the one containing 0, 1, 2, and 3, I'm going to call 4. And the next one will be 5, and then 6. As far as names go, I could have come up with anything I wanted. But these are the numbers that we use in our society. So this would be where that they originated. And that's the origin of numbers. We created them to talk about the quantity of things inside sets. As a brief side note, many people tend to think of cardinality as the number of things inside a set, as in the numbers came before. However, we have to be kind of careful when we say this, because it's not always accurate. Now, for all the examples we gave in this video so far, that would be true. And it's the case for any finite set. However, the reason that this definition using one-to-one correspondence is so important is because we also use cardinality to talk about the quantity of infinite sets. And as I've brought up in other videos, infinity is not a number. But infinite sets have a cardinality just like finite sets do. If I listed out all of the counting numbers, 1, 2, 3, 4, 5, etc., and put those in a set, then that set would have a specific cardinality to go with it. That cardinality would not be a number in the same sense that we think of numbers, but it does have a cardinality. If I took all the real numbers and pulled every number off the number line and put them into a set, then that set would also have a cardinality to go with it. And that cardinality would likewise not be a number either. So that's why we have to be careful and make that distinction between numbers and cardinality, because they're not necessarily the same thing. Thank you all for watching this video. If you enjoyed it, please like this video or post a comment below. And if you want to see more, subscribe to my YouTube channel and follow me on Twitter at Edumacator. See you next week.